Awesome. Thank you, Cassandra, for the introduction. So welcome to the NOAA Science Seminar, Intelligent Underwater Robotics, Adapting to Dynamic Environments, which will be a presentation focusing on the steps taken to create intelligent marine robots capable of adapting to environmental changes and hardware limitations. This seminar series is co-hosted by NOAA Ocean Exploration and the NOAA Central Library. My name is Nina Przinski, and I'm the Grant Science Support Coordinator working at NOAA Ocean Exploration in the Science and Technology Division, and also with the Ocean Exploration Cooperative Institute. So I'm very excited to introduce you to our seminar speaker today, Dr. Corina Barbalata. Dr. Barbalata is an assistant professor in the Department of Mechanical and Industrial Engineering at Louisiana State University, or LSU. She is the co-director of both the I-Core Laboratory and the High School Student Research Program in the College of Engineering, and she is also a fellow in the Coastal Studies Institute at LSU. She also received the NSF Career Award in 2024, and her research interests are in physics and data-driven modeling of vehicle manipulator systems, development of model-based control structures for autonomous robotic systems, and scene understanding and interpretation for robotic navigation. Dr. Barbalata served as a co-principal investigator on a project led by Dr. Catherine Skinner that was supported via the NOAA Ocean Exploration Fiscal Year 2021 funding opportunity. I also wanted to point out that this seminar builds upon the presentation given by Dr. Skinner in September entitled AI for Shipwrecks, Artificial Intelligence for Automated Detection of Shipwreck Sites from Sonar Data. So I encourage you to check out the NOAA Central Library's YouTube channel to watch her presentation as well. So now, without further ado, I'd like to thank you, Dr. Barbalata, for your time and for choosing to share your work with us today. And I'll hand the floor finally over to you now.
So thank you for the wonderful introduction. So today I'm going to talk to you a bit about what my lab is working on autonomous robots, and specifically how are we going to make them become more intelligent and more adaptable to the environment. However, this is not work that I'm doing by myself, so I'm doing with my group. So I would like to introduce what are the research areas that we are focusing on as a group. So we work generally in marine and industrial robotics, and specifically in modeling, control, and sensing for autonomous systems. Again, my group is my research associates, my PhD student, masters, and so on, without whom none of this work would be possible. Of course, we have collaborations with University of Michigan, Carnegie Mellon, or Florida State that have contributed towards this work, and this would not be possible without the funding agencies that support this work. So just to give you a bit of an insight on what we are working on, I would like to just give you a very basic idea of what type of manufacturing processes we are working on. So we are trying to move from those big robots that are used for manufacturing currently that are not safe for people to work around them to systems that are a bit more collaborative, where people and robots can work together. So one of the projects that we are working on is how would we do robots to do 3D printing without any enclosures. And we work with experts in material sciences to develop different materials for which the robots can adapt the printing performances. Another project that we are working on is how do we make multiple small robots to collaborate together for manufacturing processes among people. And here we work on perception systems, on mapping, control, and so on. So things that are small in size and people can work alongside. However, this talk is mostly focused on our marine robotics and the autonomy. So in the lab and with my students and my research associates, we are trying to work on a new development of robotic systems that are a bit smaller, and they are more affordable. So we start with system integration and customization with new sensors. Once we create this new system, we work on modeling the system, because it's expensive to just deploy the robots as soon as we build without knowing in advance how they are going to work. So we work on simulators on what are going to be the behaviors of the robots. Then we work on control and planning architecture using these models to enable the robots to operate safely and precisely. And we do perception systems. So we work with sonar images, with optical cameras, event-based cameras for these robots to understand the environment that they operate, but also return something to the marine scientists that we work on that they can use for their own research. So the whole point of doing these steps is because we want to decrease the cost of robotic systems, marine robotic systems specifically, in such a way that are more affordable for science at large and help researchers to find out more about our oceans and go deeper. So today's talk is going to be focused on how do we propose reliable autonomy architectures for systems that are small size autonomous vehicles, like the one that you can see here. This is the drop sphere, or vehicle manipulator systems. So we want to extend not only on surveying the environment with optical cameras or sonars, but we also want to start interacting with it. So what do I mean by autonomy? Basically, what we are doing in the ICOR lab, we are working on models for underwater robots. Then we are working on localization and mapping. We design control systems, planning, and perceptions. And the idea is that we shouldn't have any human input during these missions. And we want the systems to operate on themselves and react to the changes in the environment. So today's talk is going to be a very brief overview on the modeling, perception, planning, and control. However, before starting with this, just to give a small introduction on the different type of underwater robots that are available commercially. So we'll start with remotely operated vehicles. You can see here. So those are, as the name says, remotely operated. So they would need a human operator to drive the robot and take all the decisions. These are generally large in size. They require large infrastructures for deployments, although there are currently newer alternatives that are smaller, more on the hobbyist type of robots. Another type of underwater robot are the autonomous underwater vehicles, and this is the focus of my talk today. This type of autonomous underwater vehicle, the commercially available one, they are using pre-programmed missions. They do not require a tether or any of the support, and however, they do rely on the battery. So because they don't have a tether, they don't get power from the ship, but they have to rely on their batteries. And that's one of their main limitations. How do we make these robots perform longer missions while at sea? Now, if we want to interact with the environment, we have robotic manipulators underwater. So these are going to be either hydraulic, so these are going to be large manipulators, mostly placed on ROVs that put a lot of force when they have contact with the environment. Or we have electric manipulators. These ones are going to be smaller, they are going to be more precise, and they can be potentially deployed on autonomous underwater vehicles. However, there's a very limited amount of autonomy commercially available for this type of systems. So the type of robots that we are actually building in the ICOR lab, they are custom built, and we are trying to address some of the limitations of the systems that are already available commercially, because those systems are generally expensive and they are used by industries such as oil and gas or military applications. So they are not necessarily targeted toward marine scientists like ecologists, biologists, and so on. So we are trying to develop systems that are more targeted towards those type of sciences. So we want to reduce the cost, but because we are reducing the cost, that means that we are going to reduce, for example, the amount of batteries that we can put in there, so, or the type of sensors that we are putting in there. However, we still want the system to be fully autonomous and react to the environment. So this is what's going to bring some challenges to develop autonomy for this type of systems. So some of these challenges are mostly related to the environment, because when we deploy the robots, they're not always going to behave the same if I put it in a lake or if I put it in the Gulf of Mexico, right? The currents are going to be stronger. waves will be in one case, and so on. So we need to know how these robots are going to behave in these environments. We also, when we go underwater, we don't have GPS, we don't have Wi-Fi, so that means that the localization for the systems is going to be poor, and the longer time that it passes, the more inaccurate the understanding of the robot of the environment is going to be. And lastly, we have power limitations because we decrease the size, we put less batteries. So that means that the small systems will not be able to perform missions longer than 2 to 3 hours. So then we'll have to be retrieved. So how we develop different technologies and different autonomy practices to compensate for this. So I'm going to brief introduce you in how my lab is working towards advancing these states and how to address these challenges. And I'm going to start with modeling. So as I said before, when we build a robot, we can't just simply deploy it in the ocean or in a lake and see how it behaves. We have to do some studies, like some mathematical studies, to understand how is going to change the system. So for example, here, when we are saying modeling, we mean what is the behavior of the underwater robot? How does it move through the water when external forces are applied to the system? And you can see here two snapshots of our simulators. That is a synonym in our case with a model. So in here, it was like a team of vehicles surveying a shipwreck, and then the other one is how the vehicles are actually looking like. So again, moving again, so just to see those small motions. Now, when we are doing modeling, we are doing this because we want to get some insights about the behavior, but we want to help in deciding like higher level of autonomy. When we are talking about models, we are talking about physics-informed models. So these are going to be equation-based models. They are going to rely on structural analysis and sensor inputs. However, we make significant assumptions regarding these mathematical models, especially that we don't know where these robots are going to operate. An alternative to this is data-driven methods. And with the rise of machine learning and artificial intelligence, these are starting to become more popular. However, these models purely rely only on data gathered with a system. So we need a system in order to get the data, right? So it's kind of a chicken and egg problem. Now, these models are going to be only as good as the data that we are collecting, right? So they can require large amounts of data. Now, a combination of benefits, it would be to combine these two models, the physics and the data-driven model, in the hybrid physics data models. So this one, we can still use some equations, but we can improve the behavior of the models as we gather more and more data. And this is kind of what I'm going to present you first. I'm going to show you how we model the manipulator side, and then how do we model the vehicle side. So for the manipulator, what we did, we took a commercially available manipulator. It has 4 degrees of freedom, so that means 4 joints. And what we wanted to do is see if we can model based on data and some equations. So we put the manipulator on a fixed base in a water tank, but we also mounted it on a vehicle that was moving. And then we recorded data from the sensors, so that means from the encoders of the manipulator, and also from the vehicle, so the IMU and the Doppler velocity logger data. And then we use this data in order to create our models. And then we compared with the real manipulator. These are some graphs showing the behavior. So basically in blue, you can see the real behavior of the manipulator. And while in green, you can see the physics data type of model. So I have some equations, I have some data available. How do they compare? And then only the equation base is going to be seen in orange. With the physics data model, we managed to get a better behavior for the system. So the green one is following better the blue lines. And the most important thing is here we are actually, if we are starting with bad parameters, if we have an equation, we don't really know what are those parameters, we don't really know what is going on. But we still have an equation, and we start with that as a model. But as we gather data, we can improve the behavior. So this is in the right plot. You can see, again, the blue is going to be the real behavior of the manipulator, and then the green is going to be the model that we created. It starts bad because the parameters are wrong, but as we get more data and we adapt to the system, it's going to improve. With the classical approaches or just the physics informed, that is not possible. So if we start with bad parameters, we will continue with bad parameters. Now, we also did this for vehicles, right? Because we are talking both about vehicles and manipulators. And in this case, we did in water tank experiments, we did it with a 4 degrees of vehicle AUV. It was custom built, and it was the same thing. We recorded what were the velocities of the vehicle as it was performing a mission. So 4 degrees of freedom, 4 axes, and then we compared what would be a data-driven approach, and that's we use the Koopman approach actually to do that, and this is going to be the orange, and compare it with a classical approach that is just an equation-based model. So the data-driven, again, performs better, and here is just a big highlight of how different they were. So, as expected, what we concluded out of this is that if we have an equation and then we can get some data and we combine this physics informed with the data-driven approaches, we are going to improve the behavior of our models. Now, why do we use those models? First of all, to understand what's going to happen with our robot when we deploy it, but then we are also use it to design control architectures for our underwater robots. So in this case, what happens when we deploy these robots, basically, when we say we want to develop control architecture, means that we want to develop a system that is able to make our robot to go from one point to another. But sometimes there might be some delays. Maybe the sensors are not working perfectly. Maybe the computation of an autonomy stack is too slow and it's making everything slow. So there might be some delays either in the states or in the inputs of our system, of our robot. So how do we compensate for those delays? And you can see in this image, in this video, that's what's happening when our system, the control system for the robot, is not really good. It starts stable, but then all of a sudden starts shaking and is not able to maintain a constant attitude and so on. So the control architecture that I'm going to talk about has been developed for one of our robots. This is called Bruce, and you can see it here waiting for its deployment, and then during deployment. So how do feedback control systems work in general when there's no system? What happens is, like, we want to reach a certain goal, and this, I represented it with a purple. So we want the robot to reach that goal. Now, we are computing, we are saying we need this much force to be generated by our motors or by our thrusters in order to move to that goal. And this force is going to be generated based on where do I want to go and what is the current position of the robot. Once I say I compute what the force is, I tell to the robot, you have to apply this force, the robot moves, right? So as we are going closer and closer to the goal, the amplitude of the control input is going to decrease, and then the robot finally is going to reach its goal. Great. Now, when we have some delays into the system, we are computing that control input or that required force. Now, by the time we are actually asking the robot to apply that force, the robot has already moved in the future. And then again, I'm computing it, but I'm not using the current position of the robot, but something that has passed. And then I'm applying it at a later time, and so on. So what this happens, because I'm not using the correct position or velocity of the robot, is that the robot might never reach where it's supposed to be. So what we propose is, if we have some models and we know that these models are good enough, so accurate enough to represent the system, what if we can do these very tiny predictions in the future to predict where the robot is going to be? and use those predictions in order to compute the input. And then we are actually applying, right, on the real robot. So again, we do this at every single step. We do small predictions in the future where robot is going to be, and then we are applying. And by doing this, what we manage to do is avoid those oscillations in the behavior and manage to make the robot reach where it's supposed to be. So we did a statistical analysis for this. We introduced different delays in our underwater vehicle, and we wanted to see how it's going to behave. So the takeaway of this side is basically we said, okay, our proposed controller with a classical PID controller, what we managed to improve the performance. We managed to complete the task every single time. And we overall had better metrics than the classical approach. So this was for the vehicle itself. So then what we did, we also started looking in the future. What we wanted to achieve is not only to survey an environment using this vehicle system, but what happens once we want to start and interact with the environment. So in order to do that, we thought like, well, if we want to grab something from the seafloor, if that is going to be a rock or something else, we don't know in advance, or the robot doesn't know in advance what that is going to look like, how heavy it's going to be, what's going to be the shape, and so on. So we designed a control architecture that is able to compensate for these unknowns of what's going to be the payload. And the idea is that we wanted to create something that is going to be robust in terms of like accuracy and how much energy it's going to consume. So we did an optimal controller, and we did some adaptive interaction theory in order to compensate for those changes in the payload, but also changes in the flow conditions, for example. So when we tested this, what we told the robot, what the initial information knew was that it's nothing in its hand, right? So the robot goes as if there's absolutely nothing. Now, all of a sudden, there picks up a payload. So the robot doesn't know what that payload is going to be. So when we evaluated these control systems, we compare it with a classical approach. So that's going to be the left side, the model predictive control, and the adaptive neural network MPC is to the right side. So you can see that there are more oscillations in the classical one. And now showing the graphs of that, you can see that this is a 4 degrees of freedom vehicle. So there are more oscillations for the joint one, for example. With the classical approach, we do not have those oscillations. So if we don't have those oscillations, it's more stable, it's going to do the job faster, and it's also going to consume less energy. So we did all of this, and now we were like, okay, so we could deploy these robots. We know that they are going to be stable, they are going to respond to the different environmental conditions. So the next thing that we are going to look at is like, how did we use different planning architectures for underwater robots? So this is more relevant for the OER grant, and this is specifically focused on, okay, we have these robots, we know we can control them, we know that how they behave. We want to closely survey an area of interest, and we are going to equip this autonomous underwater vehicle with optical cameras. So you can see here the vehicle that we use. So this is, we call it Dory 2. It's a hybrid ROV AUV based on the blue ROV robot, and we had a stereo pair. Now, if we want to survey these like large areas, this type of small robots might not be useful. They also have to go very, very close to the seabed in order for those cameras to see what they are collecting. So it's not always efficient. So for this project, we work with Dr. Katie Skinner from University of Michigan, and she was collecting sonar data. So it was another vehicle. It was an Ivor AUV that had an EdgeTech sonar, side scan sonar, and she was collecting images that were looking like this, like the ones that you can see to the left. So we said, okay, if we have some prior knowledge about the environment, what we can do, we can start and look at the environment, detect some areas of interest, and then send this hybrid ROV AUV equipped with the cameras only in that specific area. Now, when we were looking over the side scan sonar images, we knew that there will be difficulties understanding what's the whole area that an area of interest might be, in this case, a shipwreck, because we have this dead zone at Nadir in the side scan sonar. So one of my researchers what started investigating is how can we improve side scan sonar images, and is there any type of information that we can use extra to make the system better? So we combined side scan sonar images with bathymetry data in order to create some enhanced imaging systems. So here you can see, for example, a result of those combinations. So we created a new image. It was an image with 3 channels. The first channel has integrated the sonar information. The second channel has integrated bathymetry data. And then we added a third channel where we put the quality of the data that we had. So it resulted in something like that. So now we can more better identify the area that we would like to survey. Now, we want the system to be fully autonomous. So once we identified better images that we can use, then we started looking into machine learning for autonomous detection of areas of interest. Again, we wanted to see the shipwreck. So some of my students have worked with architecture SaaS unit to automatically detect this. So in the middle, you can see the behavior of the detection when we are using that new enhanced image, so the composed image. And to the right, you can see what would be the behavior of the same machine learning technique when we are just using sonar images. So the behavior has improved. The first image represents the ground truth, so that's the manually labeled one. The advantage of this is that our data set for training this network, it was 200 images, so a very small network, and it was still capable of detecting the region. Okay, so we detect the area of interest that we have, so a shipwreck in our case. Now we want to send a small autonomous underwater vehicle equipped with cameras to go and do surveys very close to there, right? So the first question that we wanted to answer, how do we ensure that images are collected in all that area? So we started looking at different coverage path planning algorithms, um, and we generated this coverage path planning, taking into account what was the field of view of our cameras mainly. And these are some examples. What would be the coverage path planning, for example, of a shipwreck in Lake Huron? And then we compared with other approaches as well. Now, those coverage path planning, they are not really taking into account any of the environment settings, right? Or any of the capabilities, like how much battery the robot has. So in order to address that limitation, and in order to be sure that our robot is not going to hit any shipwrecks as they are doing their motion, we started also investigating in Gaussian processes type of motion planning, where we can produce efficient behaviors for AUV to actually survey the path that we generated with the coverage path planning. So these algorithms that we have been working on, they are considering the robot resources specifically, so battery life, what's the computational capability of the vehicle, and what obstacles are detected as the robot moves through the water. And the advantage is of this planner that my student has created is that it's able to actually address and do replanning once objects just pop out. So it doesn't need to know where the objects are going to be in advance, but it's able to address any new objects that are going to show up. And here, again, two different shipwrecks that we have surveyed. So we are showing the desired path versus the navigation path that the robot has taken in surveying those shipwrecks. There is a discrepancy, so you can see, for example, in the image in the middle, you have the coverage path planning is giving the red lines, and they are very, very smooth and like with sharp turns. However, when we are deploying our robots, because there's some water currents, some discrepancies, that's not necessarily going to be very, very smooth. So you will see discrepancies between the actual behavior of the robot and the ideal path that the robot should take. So lastly, we are doing this, we develop these algorithms, but the next thing is like, okay, we are actually wanting to generate something that's useful for researchers, right? And we want to deploy the system and see how they are going to behave and what type of data they are going to collect. And then we also want to create something with the data that we collect that is useful for others and not for only for advancing the autonomy practices. So some deployments that we did in the past 2 years have been in Lake Huron in Thunder Bay National Marine Sanctuary. So we did that in May of 2022 and in June of 2023. And here we deployed our underwater, like hybrid underwater vehicles, specifically Dory 2. We equipped them with a pair of stereo cameras. So these are the Blackfly S cameras. And you can see how it looks like the students are preparing the robots for the deployment. They are checking if there are any leaks, any pressure, and so on. In the second image, it's Dory as is getting ready to be deployed. And then the last one is just after the deployment is happening. So Dory was actually autonomous working during these missions. However, we still had a tether because we wanted to be sure that nothing will happen to it and we are not going to lose and we are not going to interact with the environment in any way. So this video kind of shows what Dory sees when it's deployed. And this is an autonomous survey of the shipwreck. And this is using all the components that we discussed earlier. So the control system, the planners, they are here. There's no manipulator on board, but this is kind of the quality of the images that we were getting. And these were actually good images. Okay. So once the robot is retrieved, what we are doing, we are downloading all the data that is on board of our robots, and we start like the day after, we start processing that data. So in terms of data processing, what we are doing after we collect the data, we start with image color correction because we want to retrieve the real colors of the images. And then we took those color corrected images and we are doing 3D reconstructions like you can see the one above. So, and in order to do 3D reconstructions, we are focusing on feature extraction, image matching, feature matching, structure promotion, meshing, and texturing. And then once we get those 3D reconstructions, we also kind of want to test how we scale down the reconstructions, and then we do some 3D prints. And here you can see an example of our results for the mono-handset shipwreck. And what we hope to achieve with this, like we are sharing this with our archaeology partners, and hopefully they are going to get better understanding of the shipwreck. Another example, it's can be seen here. This is a James Davidson shipwreck. This one has much finer characteristics. So the data that we were getting, it was more flat. However, we still managed to get a good 3D reconstructions, and even in the 3D print, we can see some of the features. Um, Other field deployments that we are doing, these are a collaboration with Carnegie Mellon, Florida State University, and University of Georgia. We are working on enabling these robots not only reach surface areas like the ones in the shipwreck, but we are trying to go slightly deeper. So design vehicles that are capable to go 900 meters, like 1,000 meters. So those are specifically the drop sphere and the Bruce. The drop sphere, it's a fully autonomous vehicle. Bruce, it's a hybrid remotely operated vehicle. Um, and for these deployments, we did some deployments in Miami and in the Florida Keys last year. We are trying to gather coral data, and hopefully next year we will do deployments in Hawaii to get deeper and study deep water corals. And for these ones, we are interested in environmental classifications, and we have some biology scientists that are interested in what is the quality of the deep water corals. So we start with image like color corrections, again, to better understand the environment. We do 3D reconstructions, but we are also doing classification of the different features that we are doing in the system. Now, this is work in progress. The results are still there. But the cool part is that when the robots are coming back, we also see things that did not expect necessarily to see a shark in our video. So that's pretty cool. Um, how and the last thing that I would like to show is our work that we are having using event-based cameras. So classical optical RGB cameras right now might not be very well suited for underwater environments because of the different limitations and like lack of light, backscattering, and so on. However, new technologies such as event-based cameras that are detecting motion or changes in an object might be better suited. So you can see here an example. We have a fish moving through the water. It doesn't see color or anything like that, but it's seeing clearly the direction that the fish is moving. And you can also see the surface of the water. So we are using these cameras currently to do object detection underwater, but and tracking, but also for estimating flow. And if we are able to estimate flow, then we can improve our models even better. So what is next? I talked a bit about manipulation. However, field work up to date have been focused only on vehicles and survey. We want to be able, or the scientists that we are working on would like to have systems that are small in size, that are affordable, and that are able to be deployed and not only collect images, either acoustics or optical, but also collect samples, right? So gather objects. So we are started working towards that, but there's still a lot of work to be done before being able to deploy. And when we are saying low cost, some of the vehicles that we developed with CMU and University of Michigan, so like the drop sphere, it's capable, the components are capable to reach 6,000 meters. However, the price, the building price is 35K. This is generally at least an order of magnitude less than the currently available system. And then some other examples of affordable underwater robots. So for this presentation, I would like to thank the NOAA Ocean Exploration for the support that has given for both of the grads, the collaborators at Michigan Tech, University of Michigan, CMU, Florida State University, and University of Georgia for all of their work. This would not be possible without them. But also I would like to thank very much to my students and my research associates and collaborators for all their work and for their efforts and for going field works and doing a lot of sacrifices for doing being in our lab. So thank you very much. And with that, it ends my presentation.
Awesome. Thank you so much for that. We do have some time to answer your questions. Please feel free to type them into the Q&A chat panel located on the right side of your screen, and I will upload them for our speaker to answer. Remember, your first name will show up, and you can ask questions anonymously if you choose so as well. Looks like we have one question ready to go. When initially designing these robots, was there a specific application in mind? The presentation mentions optical/sonar surveys, but with the work on manipulators, I wonder if there's a commercial use, such as for underwater construction.
Yes. So generally it's going to be for underwater manipulators. We are thinking about constructions like transportations, repair of bridges, oil and gas application, maintenance of offshore systems to not send divers anymore, but having different other systems. And for the vehicles in general, we intend like surveys of the environment specifically for data collections in terms of acoustics and optical images.
We did have a question that was entered into the audience chat asking, what do you use for the software?
So for the software, all our robots are based on ROS. So robotic operating system is the middleware that we are using to communicate between the different modules of the system. We write code, though in that ROS framework, we write Python and C++ mostly.
Thank you for that. And then our next question is, are there any specific time periods that you try to do deployments?
Yeah, so this it's always going to depend on the biologist or the archaeologist. They are going to tell us when is the best time, because they want certain environments to be observed. So for corals, for example, if they want to see coral spawning is going to happen at a very specific time, right? When we did the shipwreck surveys, we also tried just because they were in the Lake Huron, so up north in Michigan. We didn't want to be very cold and to have any ice on the lakes. So we targeted our late spring and early summer because after that, the whole environment grows and it's going to become more green towards the summer, right? So there was a very specific time. So generally, yes, it's a very specific time, but it is going to be based on the application. For the manipulation work, it has a wider range because in theory, you should be able to do maintenance work on underwater structures at any point. But if the sea is very rough, then we would avoid doing any deployments though, because we don't want to have people feeling sick or we don't want to lose anything at sea either. So we are trying to do during calming days.
That makes sense. For our next question, can you say a bit more about the motion-based camera? What's the advantage over a standard camera? What type of sensor is it?
Yeah, so they use a unique type of sensor that, so it's actually developed by Sony. So it's a specific sensor that does not require a lot of light, so it works with very light, low illumination conditions. So that's why would be better used than the regular cameras. There are only a couple of manufacturers for these cameras, so they are higher in price. But because they don't require a lot of light, they do not create images the same way that we do. They are actually very the the frames, they say that they don't use frame, but the frames that they are generated are very, very high. So they have up to 10,000 frames per second that they can generate. So those are kind of the advantages over the traditional one. But for the underwater world specifically is that they do not require a lot of light, and they do not suffer from motion blur that regular cameras do.
So, our next question is, when selecting students for your projects, what strengths do you consider most valuable? Math, physics. I am also a career coach and a student advisor.
Yeah, so very good question. So generally, if anybody, like especially in undergraduate students, if I have any student that is remotely interested, even if it doesn't have any background, then I will just take them in the lab. Like that's now as grad students, once they have to do a PhD or a master's, then I will always look, yes, for the math, physics, and if they have any experience with coding. Um, and it helps also for undergraduate students. Um, and then the other thing is, like, we do have here at LSU a high school program that I'm running. So basically every summer we are bringing a group of high school students and we pair them with researchers in different labs, and we give them some skills in order how to be better prepared in case they want to go to college or they want to go to grad schools, what we are looking for. So please feel free to reach me and I can provide you more details on the specific skills, depending.
I'm a scuba instructor. Any work planned for helping reefs and expansion thereof?
Yeah. So nothing. What we are doing with the last project that I presented, it's creating these robots that would be able to be deployed at any point without a lot of work from the people that are deploying. And the idea would be that they are going to collect images at very fixed periods of time. So you deploy over the same area, let's say every year, and you see what's going to happen and assess if there's anything. We do have other projects where we install also environmental sensors, so the pH or the chlorophyll in the water, the temperature of the water. So we do not really process and make any assessment about how that is going to impact the reefs in itself, but we do provide that information to our collaborators that this is what they are studying. The whole idea of what we are doing, though, it's trying to make technology that is affordable and has a use for those that are interested in protecting our environment.
Our next question is, if strong currents knock the robots off their predicted path, do they recover, and are there any limitations to how quickly they recover?
Yes. So the quick answer is yes, they can recover from their path. They will sense that something is wrong. They are very far away from their they were supposed to be, so they will go back. Now, when we design our robots, we don't make them very fast, so the recovery might be slow. So one issue that might happen is if they are trying to recover, first they need to assess if they have enough battery to recover and go back to the path and complete the mission. If they don't have enough battery, then they will just surface and they will say, I can't do this, right? They will send a signal to us. So it's now there might be cases where the currents are so strong that the robot, no matter how much it pushes against the currents to reach to the original path, it won't be able to do it. So it's always going to depend on the environment. But we have fail-safe mechanisms in these vehicles that if something doesn't go according to plan, what they do, they surface and they let us know that it's impossible to finish the mission.
All right. Our next question is, I'm sorry if I missed it in the presentation, but did you mention any specific programming or developmental skills for students?
So any programming language that students do that is going to be C++, Python, MATLAB, Java, any of it is a very useful skill for students to have. Knowledge in math and physics also. It's very useful for this field.
Okay, thank you. Our next question is there a maximum depth that you've been able to reach or theoretically could reach?
So theoretically, our drop sphere could reach 6,000 meters, but we've never tried it that deep. What we've reached up to now, it was 150 meters with our robots. So these are research robots also, and the thesis of my students depend on these robots. I tend to be a bit more protective and not test fully their capabilities until the students are finishing their thesis. But we are planning to do deeper exploration next year.
I have a question. Do you have a favorite robot?
Oh, no, I love them all.
You love them all?
And we try to accept the drop sphere. We kind of try to put names of our robots from Finding Dory. Or
Oh, so
so
great.
that's why Bruce was there, because it was the shark and it's one of our strongest robots.
And then we just had another question come in. What is the best way to contact you by students in other colleges who are interested?
Just email me. And yeah, emailing me, and if you have a resume, just send me that and say that you would be interested or you need help with something. Yeah. And we have, like, if anybody is interested, we are making open source all our code so we can share that with you.
Thank you all for attending today's seminar. Nina, do you have any last comments?
Yes, yeah. I just want to say thank you so much, Dr. Barbalata, for your wonderful presentation and for answering all the great questions that we received today from the audience. I also want to thank Cassandra for facilitating today. And again, I'd like to mention that Dr. Barbalata's presentation built upon the work presented by Dr. Skinner, who gave the seminar in September. So if you'd like to hear even more information about their project, please check out the NOAA Central Library's YouTube channel to watch her presentation as well. With that being said, the next NOAA Ocean Exploration Seminar co-hosted with the NOAA Central Library will be on October 23rd at 3 p.m. Eastern Time and will feature Drs. Christoph Richmond and Kelly Monteleone, who will discuss exploring inundated late Pleistocene caves in Southeast Alaska with sunfish. So make sure to mark your calendars, and I'll be sending out more information shortly. And thank you all for joining us today.